All right, this is Jack Jackson back again. We're looking at the angle side uh, condition for triangles in multiple geometries. We found that it was enough to make triangles congruent in Euclidean hyperbolic geometry. What about spherical geometry? So let's look here at this app in spherical geometry. All right, so the basic setup is the same, and we do the same construction. Pick a point here, pick a side length. We're going to actually do it side angle as before. We pick this side length. Let's make it start with something fairly small like this. And we can pick then an angle at one end, do the adjacent one here. So we know point C is somewhere along this ray here. We don't know exactly where. Let's make this a little smaller angle. Let's use an acute angle for right now. Okay, and then look at what happens next. We have to choose this point here, let it go around, and we want this ray and this line segment to be overlapping. And it looks like we get the same situation that we had in hyperbolic and Euclidean. It looks like it's happening just one place. But let's not be too hasty. Let's try some other examples. Let's look around here. Let's make this a little bit longer. Let's make this angle a little bit bigger. Try an obtuse angle. Does it still work? Yeah, looks like right in there, there was a sweet spot where it's exactly one place to make that triangle. Okay, but I want to show you something. If this gets too big, then there can be more than one spot. And I have a specific example that I want to look at. There's the equator and the poles. Let's put, excuse me, let's put A and B on the equator. Okay. And let's pick these to be pi over 2 for both angles. Let's see how I want it. Well, I want to do that. I want to choose. Let's see where C could be. We may or may not get that to work. So there is a place here that if I make this long enough, okay, that things start messing up. So if this is bigger than, let's make this be pi over 2, also in length. And if you look, here is one where if you're at the North Pole and these 2 points on the equator, what do we get? We get pi over 2 here. What I want is, okay, I want A and B. I want A, here's the example I want. I want A to be at the North Pole, and I want B to be on the equator. And notice that I can get, no, I want it the other way around. Okay, here we go. I think this is going to give me what I want. I want A to be on the equator, and I want B to be at the North Pole. okay, which I can do if that length is pi over 2. I don't know if I have it perfectly, but it's pretty close. Okay, but now what I want you to notice here is this C can be anywhere along here, and it will make angle C pi over 2. Check it out. See that? So there are actually all of these triangles here that I'm looking at as I move C around have, look at they have angle, angle, and a side. Blue side's the same. The angles are both pi over 2, but look what happens to the other, this green side. It could be any possible length. So there's actually infinitely many different congruence classes there. So yeah, it's a little different here in spherical geometry, right? So if the triangle is small enough, if you can guarantee that all the sides have length less than pi over 2, so the whole thing could fit into one octant of the sphere, then the angle side in spherical works exactly like it does in Euclidean and hyperbolic geometries. It is enough to make the triangles congruent. It is exactly one congruence class. What's a little different is, though, if you don't put that restriction, there are cases here like this one where you could have infinitely many different triangles, including one somewhere here where all three of the angles are right angles. Okay, so that's interesting. Another thing that's a little different here in the uh, Euclidean and hyperbolic cases, the interior angles have to add up to pi in Euclidean and less than pi in hyperbolic. So if the two given angles already add up to pi or more, there was no triangle possible. Well, that doesn't happen here because in spherical geometry, the angle measures add up to more than pi but less than 3 pi. So you can actually give any two measures of the angles that you want, and there is a triangle possible. So there is not a zero congruence class possibility for spherical geometry. There's either one or infinitely many, depending on the measurements. So kind of crazy, huh? In fact, this one's even worse than that if you think about it, because not only does this violate angle, angle, side, it actually violates angle, angle, side, side, right? Because all of these here have, these are actually isosceles triangles. The red side here going from the North Pole down to the equator from B to C, and also going from the North Pole to the equator going from B to A. Those are both lengths of pi over 2 spherical units. A spherical unit is the distance from the center of the sphere to the sphere itself. As a Euclidean distance. So if you take that as a length of 1, think of this as a unit sphere, right? Then the distance here is just that Euclidean arc length, which is pi over 2. So this pi over 2 is a distance. These pi over 2 are radian measures of angles. Okay, so in any event, we see that these triangles like this one and then this one have these two sides congruent. The blue side here is congruent to the blue side here. The red side here is congruent to the red side here. And the angles down here and here are congruent to their corresponding ones in the other triangle. So we see that they satisfy the AASS condition, but that's not enough. So here's an example where we have 4 things that are congruent in spherical geometry, but that's not enough to make them congruent. Another thing that's really unusual here about spherical geometry is notice that if you look at an exterior angle, this angle right here, it's a right angle, and it's the same size as, say, this angle over here. That doesn't happen in Euclidean and hyperbolic geometry. In hyperbolic or Euclidean, the exterior angle is strictly greater than each of these remote interior angles. Now, it turns out that if all the sides are small, again, where we fit into one quadrant, okay, one octant, right? I can turn this off. That in fact the exterior angle here you can see the larger angle here, it is greater than each of the remote interior angles. So uh, that's going to help us get to the situation where we're going to prove the exterior angle theorem in just a bit, and then we'll use that to prove the angle side theorem. But both of those things are not always going to work in spherical geometry. They'll only work in spherical geometry if we have a restriction on the size of the sides of the triangles. So interesting. Uh, Hyperbolic and Euclidean geometry so far seem to be acting pretty much the same in terms of triangle congruence. Spherical almost the same, but a little different here when it comes to AAS property.